I'm going to go over the homework on permutations and combinations and all the problems that I didn't solve in the notes. So the first part here is on factorials. Factorials an exclamation mark, and on number 2 we wanted to simplify it in lowest terms. And so it's a fraction. We want to reduce this fraction as much as possible. 1 factorial is just 1. I want to show you something over 2 factorial. Well, there's a pattern here. If we look at 1, I'm going to split this up. If we look at 1 factorial over 2 factorial times, and then we're going to have 4 factorial over 3 factorial, and then 5 factorial over 6 factorial, and so on. And we continue that. But here's what I want you to see. If I have 1 factorial over 2 factorial and simplify that, that's going to be 1 over 1 times 2, which is 1/2. If I have 4 factorial over 3 factorial, that's going to be 4 times 3 times 2 times 1 over 3 times 2 times 1, which is 4 over 1, or just 4, after you reduce this fraction. If you have 5 factorial over 6 factorial, that's 5 times 4 times 3 times 2 times 1 over 6 times 5 all the way down. And you reduce this, and you end up with 1 over 6. And so knowing that, you can continue to reduce. So after 5 factorial over 6 factorial, you have 8 factorial over 7 factorial, and if you expand that and reduce that, you're going to end up with 8 over 1. And then after that we have 9 factorial over 10 factorial. If we wrote all that out and reduced it, we'd end up with 1 over 10. And then after that we have 12 over 11. It's going to give us 12 over 1. And then last one is 13 over 14, which is 1 over 14. Okay. And then we can start to reduce this fraction. You can, let's see, 2 times 6 is 12. And so if I just gather together what's left, we got 4 times 8 over 10 times 14. And continue to reduce. I could divide by 4 and take a 2 out of the 10 and take a 2 out of the 14. And we're left with 8 over 35. And that is about all we can do. And that is our answer. So just got to work through that, reduce, and we got it. Number 3, we have n factorial times 5 factorial equals 6 factorial. So n factorial times 5 times 4 times 3 times 2 times 1 is equal to 6 times 5 times 4 times 3 times 2 times 1. Divide both sides by 5 and 4 and 3 and 2 and 1, and we're left with n factorial equals 6. Now if you break up 6, you get n factorial is 6 is 3 times 2 times 1, and that's the same thing as 3 factorial. So we have n factorial equals 3 factorial. That means that n is 3. Then we start looking at a permutation and a combination. Permutation is an arrangement of objects, where a combination is a group. We have a formula for permutation here that you can use. Often I won't be using this formula because, well, you'll see as I work through the problems, it's often not needed, but it does work. Sometimes you do need it, but let's take a look here. I answered 5A and 5B, and sorry, 5A and 5C, and we're going to look at 5B. And this is with letters and how many different rearrangements of the letters can you have. Doctor has 1, 2, 3, 4, 5, 6 different letters, and so we have 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1, over, and you look for repeat letters. We have 2 O's, so we're going to divide by 2 factorial, and that's the only repeat we have. And so we just work through this, find out what 6 times 5 times 4 times 3 times 2 times 1 is, divided by 2 times 1. And after you work through that, you're going to end up with 360. Number 6, you have 30 people are running a race. In how many ways can people win first, second, and third place? So you have 30 options for first place. Once you give that first place away, you only have 29 options for second place, and then you have 28 options for third place. So I'm using the fundamental counting principle there, and we end up with 24,360. Number 7, how many ways can we arrange the letters of the word system? Again, here you count how many letters you have, 1, 2, 3, 4, 5, 6, divided by, and you look for repeats. So I have 2 S's, and those are the only letters that are repeating. And then I reduce that, and this ends up being the same as part B in number 5, which is 360. Right there. Number 8, and how many different ways can the letters in the word study be ordered? Study has 1, 2, 3, 4, 5 letters, and none of them are repeated, so it's just 5 factorial, and 5 times 4 times 3 times 2 times 1 ends up being 120. Extra credit. How many 3-letter words can be made from a 4-letter alphabet? So let's say our 4 letters are A, B, C, and D. So you have words where all the letters could be the same. So you can have all of them being A's. That would be a 3-letter word. Or all are B's. And when we say a 3-letter word, it does not have to be a word that is in our dictionary or anything like that. It's just a combination of letters. So there's 4 different ways to have repeats, right? And then we got to think, well, how many different ways can you have 2 A's, right? So if I have 2 A's, I can have A, B, or I can have A, B, A. Or I could have B, A, A, So those are the three different ways that you can have two A's. Well, actually, sorry, that's with B. That's with A and B. You can also have, you can replace the B with a C and have AAC, ACA, and CAA. And you can replace the C with a D and have AAD, ADA, and DAA. Okay, so there are 9 ways for 2 A's, but then there's going to be 9 ways for 2 B's. There's going to be 9 ways for 2 C's, and there will be 9 ways for 2 D's. So we have, we've found out like how many 3 of a kinds you can have. There's 4 3 of a kinds. How many 2 of a kinds? So that's 9 plus 9 plus 9 plus 9, which is 36 ways. And then 1 of a kind, so you can't repeat anything. And this one's a little easier for us. If we're going to pick 3 things and we can't repeat, we have 4 options for our first letter. It could be an A, a B, a C, or a D. We have 3 options for our second, and we have 2 options for our third. So there are 12 ways to 12 ways to have no repeating letters. Okay, so we're going to add all that up. So our answer is going to be 4 plus 36, that's your 4 9s, plus 12. And I'm getting 52 as an answer there. And actually, I just found that I made a mistake. 4 times 3 times 2 is not 12. That should be 24 ways. And so I'm going to change that 12 to 24. And instead of 52, we're going to end up with, let's see, 64 ways. That's our answer for number 9. Number 10. How many ways can the letters in math be rearranged? You have 4 letters, so we got 4 factorial. And we have no repeats, and so our answer is just 4 factorial, which is 4 times 3 times 2 times 1, or 24 ways. Number 11, the words or the letters in the word mathematics can be arranged in 11 factorial over x different ways. Find out what x is, or determine x. So mathematics, if you count, has 11 letters in it. And we're going to divide by repeats. And notice the 11 that I put in the numerator matches the 11 in the numerator over here. And so what I get in the denominator is going to be x. So I'm looking, I have 2 m's, so 2 factorial for the m's. I have 2 a's, one here and one here. I have 2 t's, one right here and one right there. And I think that hits everything I need. So x is going to be 2 factorial times 2 factorial times 2 factorial, which ends up being 8. Alright, going on. Here's the combination formula that you can use. Notice a combination is a permutation divided by some factorial. or you could just have the full-blown combination formula here. So number 13, I think I worked through with you already, but if I didn't, or if I'm not remembering correctly, your answers should be 45, 35, and 4. And you just plug in N and R into that formula and it should work. Okay. Tell whether each of the following is a permutation or combination. I think I did a couple of these with you, but I'll go through these. I'll go through all of them. So on A, if ever you see the word arrangement, by default it's a permutation. If ever you see the word committee, okay, so we got arrangement means permutation. If ever you see committee, that's gonna clue you into we're dealing with a combination. Because in an arrangement, the order of things matters, and that's key to permutation. In a committee, the order in which you select the committee does not matter. It's just what's the group you have. I don't care who you picked first, second, third. So that's where combination comes in. If you worry about who's first, second, and third, like on part C, then order of selection matters. It's a permutation. D, selecting a photo for a photo book front cover and one for the back. So in this case, order does matter because it is going to matter what's on the front and what's on the back, so that's a permutation. Creation of a telephone number, yes, it matters if what your first and second and third numbers are, so that's a permutation. F, determine the batting order for 9 players on a baseball team. Again, the order is going to matter. You want to strategically place your batters on, number 1, number 2, number 3 batters, and so on. Answers on a true and false test. Yeah, your answers are going to matter. Question number 1 is going to be different than question number 2, and so that would be a permutation. Creating a dish of ice cream with 2 scoops chosen from 31 flavors. Here, I think order is not going to matter. I mean, maybe someone's really picky and they want certain flavor ice cream to be below the other one, but in general, people are not going to be picky. This is going to be a combination. Because it doesn't matter which scoop, like if you had chocolate and vanilla, it doesn't matter which one you got first. For I, the selection of 3 books from a collection of 20 books. Again, it's not going to matter which book you pick first or second or third. It just matters what 3 books you end up with. And choosing 10 items at a grocery store doesn't matter which item you get first, second, third, and so on. It just matters that you get the correct 10 items that you went out for. So combination. We have 15. 16. A smoothie place has 10 kinds of fruit. How many different smoothies can be made if each one has 4 different fruits in it? Okay, so you're going to create a smoothie. You're going to pick 4 fruits. So I'm going to pick 4 things. And our first option, we have 10 different kinds of fruits to pick from. So 10 options, and we're going to assume we're getting different fruits. Okay, it has 4 different fruits. Actually, not assuming, it says that, so you can't repeat the fruit. So once you use 1, you only have 9 left over, and then 8 left over, and then 7 left over. Now, this is using the fundamental counting principle, and if the order in which you pick the fruit matters, then that would be the answer. If the order doesn't matter, if it's a combination, then you're gonna divide that product by how many fruits the factorial of how many fruits you picked. So I've picked 4 different fruits, and there we have it. Okay. So this is the format of a combination. The permutation is on top. It's the 10 times 9 times 8 times 7. That's if the order mattered. Because the order doesn't matter, we're dividing by how many things we pick factorial. When you work through the math on this one, and you can use your calculator, or you could just reduce it. Let's see, 10 times 9, 8, 7 over 4 times 3 times 2 times 1. You could say 4 times 2 is 8. You can divide 9 by 3. And you're left with 10 times 7 times 3, which is 210. So you could do it without a calculator like that, or you're able to use a calculator as well. And you get 210 different ways. 17 and 18 we did. 19, a dodgeball tournament requires teams of 4 students and 2 teachers. If 10 students and 3 teachers agree to play, how many ways can a team be picked? So you have 2 separate problems here. So you have the student problem, and you're picking 4 students out of 10. So I have 10 options, and then 9, and then 8, and then 7 options. But the order didn't matter, so I divide by 4 factorial because I picked 4 students. And then you have the teachers. And for teachers, I'm picking 2 teachers out of 3 teachers. So I have 3 options for my first pick, 2 options for my second pick. Again, order didn't matter. I picked 2 teachers, so it's out of 2 factorial. So I have how many students, how many teachers, and I'm going to end up multiplying those together to get my final answer. The student one kind of matches the exact math we did in 16, and so for students we get a 210. For teachers, this one's not too hard. 2 factorial is 2, so we're going to end up with 3 different ways. And then you multiply those together, 210 times 3, and you're going to get 630. Alright, moving on. Number 20. We have AP students are given a list of 9 books for summer reading. How many ways can 5 books be selected from the list? Okay, so we're going to select 5 books. Order doesn't matter, out of the 9. So my first selection I have, so I'm picking 5. I have 9 options for my first, then 8, and then 7, then 6, and then 5. And I've picked 5 things. Order doesn't matter, so I divide by 5 factorial. Plug that into your calculator, and you're going to get 126. 21, quality control for a Sharpie company tests 2 out of 150 pens. And how many ways can those 2 pens be selected? So I'm selecting 2. I got 150 options for my first selection, 149 for my second selection, and it doesn't matter what order I select them in, so divide by 2 factorial. Again, once you work through this, you're going to get 11,175. Sorry, I forgot my 7 here. Next one, number 22. 100 students qualified to run finals at Woodward Park. And how many ways can first, second, and third be awarded? So now order is mattering. So this is a permutation. You have 100 students that qualified. So 100 options for first place times 99 options for second place times 98 options for third place. And you're going to get a big number. You get 970,200. 23, a teacher, her aide, and 5 students are lining up. How many different ways can they line up? If the teacher must be in the front of the line and the aide must be in the back. Okay, so I'm going to put T in the front, and then you have 5 students, and then you have this aide in the back. Okay, and there's only one teacher and there's only one aide. Well, how many different ways can you select the teacher? Only one. And then how many different ways can you pick a student? 5. And then 4. And then 3, 2, 1. And then how many different ways can you pick that aide? There's only one aide. So you multiply those numbers. Again, this is using the fundamental counting principle here. And so you're going to get 5 factorial. What's that going to be? Let's see. We got 20 times 6, so 120 ways. 24, John goes to the store to buy ketchup, mustard, mayonnaise, barbecue sauce, tomatoes, and lettuce. He realizes he only has enough money to buy 3 of the items. How many groups of 3 items are possible? Okay, so how many items are there? So there's 1, 2, 3, 4, 5, 6 items, and he's only going to pick 3. So he's got 6 options for the first, 5 for the second, 4 for the third. But it doesn't matter what order he picks those in. Like if he got maybe ketchup, mustard, and mayonnaise, say those were his 3, it doesn't matter if he picked the mustard first or the ketchup first or the mayonnaise first. It just matters that he got those 3. That's what makes the group. So I divide by 3 factorial. And so for when you work that out on number 24, you end up with 20 different ways, or groups of 3. 26, tablet comes in 32 gig, 64 gig, and 128 gig with color options black, white, red, and blue. It also comes with or without cellular data capabilities. How many unique tablets are possible? So in this one, well, you're gonna pick a size out of 3. So you got 3 options for size. You're going to pick a color. You got black, white, red, or blue, so you got 4 color options, so times 4. And then you have cellular or no cellular, so there's 2 options with cellular, and so then you multiply that together. And on 26, you're going to get 24 different combinations here. 27. How many distinguishable permutations of the letters needed are possible? And we have 1, 2, 3, 4, 5, 6 letters. And then you look for repeat letters. So we have 3 E's and 2 D's. So over 3 factorial, 2 factorial. And that comes out to be 60. Number 28, how many 6-person squads can be made from a team, I should say from, not form, sorry about that, from a team with 10 people. So you have 10 people, you're choosing 6 people, so you got 10 options, and then 9, and then 8, 7, 6, 5. So there's 6 options, and the order didn't matter. So over 6 factorial. And you will work through that, reduce that, and you get 210. Number 29. Ella has 10 crowns to color a map. She knows she only needs 4 of them. How many ways can she choose 4 colors? So she's got 10 options, and then 9, 8, and 7, but order doesn't matter. Work through that, and again, you end up with 210. Number 30. How many 4-digit numbers are there whose digits alternate between odd and even? So you have two cases. You could be even, odd, or we can have odd, even, odd, even. Doesn't say what it starts with, it just says it alternates. So your even digits are 0, 2, 4, 6, and 8. Your odd digits are 1, 3, 5, 7, and 9. So if I'm going to have a 4-digit number starting with an even number, notice you can't start with a 0. If you start with a 0, it's not going to be a 4-digit number. So you actually only have 4 options when you start a number off that has an even digit. Odd, you got 5 options. Even, you got 5 options. Odd, you got 5 options. With 4-digit numbers, you can repeat a digit, right? You can have 4,555. That's a number. You can repeat stuff. Odd, you got 5 digits you can start with. It doesn't matter, 1 through 9. Even, 5, 5, and 5. So you find out what these are. So you multiply this together, add those up, and you end up with 1,125. Again, it's okay to use a calculator. Number 31. How many 5-person squads can be made from a team with 9 people? Okay, so we have 9 options for the first pick, and then 8, 7, 6, and 5. I've chosen 5 people. Order doesn't matter, so I chose 5 people. So over 5 factorial, you end up with 126. Ben & Jerry's Homemade and Company sells 20 different flavors of ice cream. How many 3-dip cones are possible if order of flavors is to be considered and no flavor is repeated? So you got 20 different flavors of ice cream. We're picking three cones. Okay, no flavors are repeated. So we got 20 options for the first, times 19 times 18, and the order doesn't matter. And so this is what I want. If you work through that, and you can get an answer, because right now it doesn't seem to match anything, although it does match one of these. But if you work through it, you're going to find out which one it is. And sorry again, this should be letter A, not a B. And if you try, these actually are going to be equal to each other. 2 ways to tell. One, you can plug each one into a calculator and find out they're the same value. The other way is to see that this is 20 times 19, 18. If I make this 20 factorial all the way down to 1, I have 3 factorial already, but then what wasn't there was the 17 all the way down to 1. And notice that that is 17 factorial. So this divided by 17 factorial, this piece right here, is what I added, but you can do that with a fraction. You can multiply the top and the bottom by the same number and the fraction's equivalent. So by doing this, notice now the top goes from 20 all the way down to 1, so that's 20 factorial, and the bottom has 3 factorial, 17 factorial, which is exactly what we have here. It's okay if you don't make that connection. You don't have to make that connection. Just use your calculator, plug it in, see what each one's equal to, and see that they're both the same. All right, 33. Sorry, 34. 33. A set of books, and again, I have my lettering off here. A set of books can be arranged on a shelf 120 different ways. How many books are there? So, if you have an arrangement, it's a permutation. Let's say, uh, say the one we don't know, but say there's n options, and so we're going to have n factorial different ways is equal to 120. And 120, if we break that down, well, 120 is 12 times 10. Keep breaking that down. You get 6 times 2 times 2 times 5. And 6 is 3 times 2. Alright, so I just broke 120 down to its primes. 3 times 2 times 2 times 2 times 5. Now, I'm going to try to rewrite this as a factorial. So that's equal to 1 times 2, and I'm going to grab that 2 right there, times 3, use that 3 right there, times 4. To make 4, I need to multiply the 2 and 2 together, times 5, and notice that that is 5 factorial. So 120 is 5 factorial, and so 5 is going to be our answer. If you want to check this, you can think, okay, if I have 5 books, how many different ways can I arrange them? You say, well, I have 5 options for the first spot, 4 options for the second, 3 options for the third, 2 options for the fourth, and 1 option for the last. And that gives you your 5 factorial, gives you 120. It works out. 34. In how many ways can 6 people be seated in a circle? If 2 arrangements are considered the same whenever each person has the same neighbors, not necessarily the same side. So here, I'm going to draw our 6 spots here. Okay, so let's look at one arrangement. So A, B, C, D, E, F. Okay. And so you might say, hey, there are 6 different spots here. And so like where I put the A, if there are 6 people, how many different people can I put in spot A? Well, 6, right? So we got 6 options for A. And then once I put someone there, how many options for B? Well, 5. How many options in seat C? 4. D is 3. E is 2. And F is 1. But that's if we were thinking linearly, because we have 2 things, we have something else to consider here. What if, if you picture this as a bracelet here, okay, with these different beads on them or something like that. If I flip the bracelet over, still the same bracelet, but A and D would be in the same spots, but B would be over here, F would be over here, C would be over here, and E would be over here. So you have the same people sitting next to each other, or if it's a bracelet, you have the same beads next to each other, but the bracelet's been flipped over. And so for every combination, there's this reflection that you can have, and so we're going to have to divide by 2 to represent the reflection, because if we don't, we're going to have twice as many that are repeats. For example, if I listed all these ways out, I would have both of these in there, and they would actually represent the same thing. So I have duplicates, and I don't want to double count everything, so I need to divide this by 2. So that's the reflection. Not only do we have to worry about reflections, but what about rotations? So again, what if I let's say I take this bracelet that the one I'm putting a square around here, and left it like that, but I just rotated it once so that the B was on top and the A moved over here, and then the F, E, D, and C. So it's still the same bracelet. It's still, every letter A is still next to B and F. F is still next to E and A, and so on. It's just been rotated. And how many different rotations can we have? Well, we can have a rotation where A is on top, one where B is on top, one where C is on top, one where D is on top, one where E is on top, and one where F is on top. There's 6 letters, so 6 different rotations. And again, if I were looking through a list of rotations, all 3 of these are the same, right? And there's 6 different rotations, and so I also have to divide this by 6. And so that's what we end up with. So this is a little trickier because you have to think about rotations and reflections, and you work through that and you end up with 60. It's a tougher problem, but it's an important problem to go back to, think about. If you changed up the numbers a little bit, what would happen? Again, think about rotations, think about reflections. Number 35. 3 math books, 4 physics books, and want to arrange on a shelf so that all the math books are together and all the physics books are together. Okay, so we can have math first and then physics, or we can have physics first and then math. If we have math first, I'm going to use all of them, right? So I got 3 options, and then 2, and then 1. And then I got to use my physics, 4 physics books, and 3, then 2, then 1. Or, when I say or, I'm going to use a plus sign. Physics first, so I got 4 physics books, and then 3, 2, 1. And then math, I got 3 math books, 2, 1. There's 7 books in total. You're going to line up all 7. So you're going to find these 2 products, add them together, and after we do that, we end up with 288. Last problem. 6 people are at a meeting. At the end of the meeting, each person shakes every other person's hand exactly once. How many handshakes take place? So, when 2 hands shake, right? Let's pick one hand. Let's think of one handshake. How many different one handshakes are there? Well, there's we're just going to assume maybe they all shake with their right hand, okay, or that kind of thing. But or it's just really from who, right? If you pick 2 people to shake hands, let's think about that. Don't worry about the handshakes. Pick 2 people, and there's 6 people total. So if I want 2 of those people to shake hands, I have 6 options for the first person, and I have 5 options for the second person. But it doesn't matter who I picked first and who I picked second. Like, say I picked Joe first and Sarah second. That'd be the same handshake as if I picked Sarah first and Joe second. So I need to divide by 2 factorial. It's a combination. So we had 30 over 2, which is 15 different handshakes. There you have it. Again, if you have any additional questions about this, please feel free to email me, and I'd be happy to answer.